Welcome to the Explainer. Have you ever looked at one of those simple drawings, the boxes and lines, and wondered how in the world that turns into a powerful working database that can handle millions of records? Well, today, that's exactly what we're doing. We're going to break down that process, turning a conceptual blueprint into a logical, structured database.
Okay, so let's just dive right in. The central question is this: what is the magic here? How do you translate an abstract idea, an entity relationship diagram, into something a computer can actually understand and use to store and retrieve data efficiently?
You see, it's really all about translation. On one hand, you've got the diagram. It's visual, it's intuitive, it's made for us humans to understand. And on the other hand, you have the relational schema, which is what the database actually needs. Our job is to follow a set of rules to bridge that gap.
All right, so first things first, let's lay the foundation. Before we can even think about connecting stuff, we've got to map the most basic pieces of our diagram, those core entities and all their descriptive attributes.
And the process starts out pretty simple. A regular entity, something like customer, well, that just becomes its own table. And say you've got a composite attribute like name that's made up of first underscore name and last underscore name, no problem. You just break it apart. Each little piece gets its own column in the table. See? Nice and straightforward.
Okay, but it's not always that simple, right? Things can get a little tricky. What happens when one attribute needs to hold multiple pieces of information for the same person? Think about it. An employee might have a work phone, a cell phone, maybe a home phone too. You can't just cram all of those into one single box, can you?
Well, the solution is actually pretty elegant. You create a brand new table just for those multiple values. And here's the clever part. To make sure every single entry is unique, the primary key for this new table is a combo. You take the original ID, like the employee's ID, and you pair it with the attribute itself, like the specific phone number. That way, every single phone number is perfectly tied to one and only one employee.
And here you can see that rule in action. Our one little employee entity, it's just beautifully blossomed into two connected tables. We get our main employee table and a separate employee_phones table. This new setup is so much better. It can hold as many phone numbers as you need for any given employee, all without messing up the structure.
All right, so we've got our tables. But right now, they're just kind of floating there. They're like isolated islands of data. The real magic, the real power, happens when we connect them. So that's what's next. Mapping the relationships.
Now, for the most common relationship out there, the one-to-many, there is one golden rule. Seriously, you have to remember this one. It's a simple idea, but it dictates everything about how these tables link up.
So picture this. One department has a bunch of employees, right? A classic one-to-many. To link them up, it's simple. You take the primary key from the one side, that's the department ID, and you just drop it right into the employee table. It now becomes what we call a foreign key. It's like a little signpost, pointing every single employee back to their home department.
Okay, but what about one-to-one relationships? They're a little different. Like, say, a manager who runs exactly one department. When you map this, you've actually got a choice to make about where that connecting key is going to go.
So how do you choose? Well, the best practice all comes down to something called participation. If one of the tables has to be in the relationship, we call that total participation. Then that's where you put the foreign key. So if every single department must have a manager, you put the manager's ID in the department table. Why? Because it guarantees that column will never be empty. No nulls! It just leads to a much cleaner, much happier database.
And now, for the big one, the many-to-many relationship. This is where many students can sign up for many courses, and those courses can have many students. You absolutely cannot just stick a foreign key in one table or the other. It just doesn't work. It would completely break the model.
So what do? The solution is to create a brand new table that just sits right in the middle. People call this a junction table, or sometimes an association table. Its entire job is to be a bridge, connecting those two original tables. This registration table is the perfect example. Look what it does. It grabs the primary key from the student table and the primary key from the course table and uses them both as foreign keys. Then you combine them, and that combo becomes the new primary key for the registration table itself. It's brilliant. It perfectly tracks every single student to course connection. Okay, our foundation is looking really strong. So now let's get into some of the special cases you're definitely going to run into: weak entities and these inheritance structures. A weak entity is pretty much what it sounds like.
It's an entity that just can't exist on its own. Think of a dependent in a company database. That person only exists in the database in relation to an employee. I like to think of it like this. It's a room in a house. The room can't just float in midair. It has to be attached to the house. Its very identity is tied to its owner.
So check out how this gets mapped. The primary key for this new dependent table isn't just one column. It's a composite key, a combo key. What it does is it borrows the primary key from its owner, in this case the employee ID, and it combines that with its own little identifier, its own partial key, like the dependent's name.
All right, last big concept, inheritance. You might also hear this called specialization or generalization. This is how we model those ISA relationships. You know, where a car is a vehicle or a truck is a vehicle.
So when you need to map this kind of inheritance structure, you've basically got three main choices. You could create one giant table for everything. Or you could have separate tables for each subtype that link back to the main one. Or you could just create tables for the subtypes, and that's it. Each way has its pros and cons, and honestly, the best choice really depends on your specific data and what you plan to do with it later on.
Wow, so we've gone all the way from a simple drawing to this intricate web of interconnected tables. Let's boil this all down. What are the absolute key takeaways from this whole blueprint?
Okay, remember these. These are the core principles that will get you through pretty much any mapping problem you'll ever face. Entities, they become tables. Relationships, you build those with foreign keys. That tricky many-to-many relationship, it always gets a new table, no exceptions. And weak entities, they borrow their owner's key to survive.
When you really get down to it, if you remember just one thing, let it be this: primary and foreign keys. They are the absolute nuts and bolts holding your entire database structure together. Everything depends on them. So you follow these rules, you get this perfect, beautiful, logical structure. But, and this is the big final thought, you've mastered the blueprint for a perfect world. What happens when messy, inconsistent, real-world data shows up and just refuses to fit into your perfect plan? Something to think about, right?